day everyone, and welcome to the second session of Physics for Grade 12, in which we are going to continue the chapter 13, Light Diffraction. Before we move on to this session, let's go over the first session and talk about the basic notes that we have reached. We talked about electromagnetic waves, about their properties, speed, wavelength, frequency. We also went to diffraction of waves, and we focused on the law of diffraction for light, which is A sine theta m equals to m lambda, where m belongs to z star. So this law gives the angular deviation or abscissa of the center of a dark fringe of order m. We also went to a small angle approximation in which sine of the angle of a certain angle is almost equal to tangent of the same angle, is almost equal to the angle as expressed in radians, and we talked about the geometry of the figure of any pattern of diffraction. Now, we're going to use these to review more by solving the application that I have suggested last time. So, please prepare your homework. Anyone who solved the exercise, have it ready on you now, because we're going to discuss it. And if you haven't solved it, let's go over the discussions. So first, the application was a monochromatic light of wavelength 587.5 nanometers illuminates a slit of width 0.75 millimeter. At what distance from the slit should a screen be placed so that the first dark fringe is at 0.85 millimeter of the center of the diffraction pattern? So, one question, okay? How would you solve this exercise? Some of you might go to an equation which we have memorized, but as I said, we can't go to the equation giving the abscissa. When we solve such an exercise, first thing we start with is drawing a very clear figure. Now here I have a figure which is drawn, and I've taken a lot of time dealing with this figure. You can just draw it roughly. It's important to show the dark fringes, and in particular the first dark fringe. So we start by the diffraction law, in which A sine theta equals m lambda with the condition on m. The first dark fringe is what we're studying, so m equals to 1, sine theta equals lambda over A. Now, lambda over A is very small. I used the values here, 0.0008, which is much less than 0.173. Therefore, small angle approximation is valid. Now, this idea here, okay? Now, it's not obligatory, honestly. Since in diffraction we always have small angles, if you just omit this, it's fine. I just added it for those who need to be accurate and precise about their calculations. Okay? So, a small angle approximation can always be used. It's always valid. Now, by trigonometry of the triangle IOM, we said that every time we need to link distances to angles, we need trigonometry. So, we specified the right triangle, IOM. By trigonometry in this triangle, we have tangent of the angle theta, theta 1, I can add this here, which is OM over OI according to the figure, where M is the center of the first dark fringe. Then tangent theta is X over D. It's covered by this part here. Anyway, now, but since sine theta is almost equal to theta because we are dealing with small angles, therefore we can say that lambda over A, where is it? Here, is equal to X over D, which is covered by this part here, so I will replace it down. Okay? Now, setting small angle before this, or if you reorder these, it's fine. Okay? It's okay. Now, then, regrouping this equation, D equals AX1 over lambda, replacing values. Here I need to note or point out units. I have written units here, okay, so that when I continue calculations, I need an answer in SI unit or in some particular unit. So converting all units to meters from millimeter 10 minus 3, as we know, nanometer 10 minus 9, I got D equals 1.09 meters. So I think most of you got the answer correct. If you have any question or any comment about this question, please refer back to your teachers or write them in the comments. Now we proceed. So in diffraction, the main target, أهم شيء بيهمنا ندرس بالديفراكشن قلنا كل هالباترن حكينا عنه بس أكثر شيء مهم هي central bright fringe. So بهي السكشن رح نركز على the central bright fringe of interference. The central bright fringe of of diffraction. The central bright fringe of any diffraction pattern is bounded between the two dark fringes of order +1 and -1. So I've drawn the figure here, the central bright fringe. This is the dark fringe of order m equal to +1, and this is for m equal to -1. Now the figure is symmetric, and L equals 2x1. Okay, so it's enough to study one part and multiply by 2 whenever we need to calculate L or anything like that. So we take tangent θ1 equals x1 over d. We already know that. By the diffraction law, sine equals lambda over a. I went quickly over these. Small angle approximation, so these are equal. Sorry if I'm moving fast, because this is a simple application of what we have seen previously and in the previous application as well. So combining these two, we got x1 equals lambda d over a. Now replacing, if you want to find L, the linear width, as we have said previously, the linear width of the central bright fringe is given by this equation. Now, can we memorize this equation and use it? Honestly, no. In official exams, any question will always ask you in steps, and we'll see an example, to reach this point. But memorizing this makes things easier. Most probably, if you are rushed up in time, you can write the rule. If you go to higher levels and you have multiple choice questions, you might use it directly. So yes, add this rule to your equation bank. Okay, it might be handy somewhere, and if it's not useful, it won't cause any harm. Okay, so the central bright fringe is important. We need to know how to find its linear width. We need to know how to find its angular width, which we haven't found yet. But I think it's easy if we just combine θ1 to anything else. We know that alpha is 2 θ1, right? So here I write it. And the angular width alpha, which equals 2 θ1, equals either 2 times x1 over d or 2 times lambda over a. Okay? Now, another factor we talked about, we introduced when we were studying diffraction. Okay? Now it's time to talk about it. It is the intensity, the luminous intensity of the diffraction pattern. Luminous intensity is the amount of light that you can observe in a certain spot or in a certain fringe. If you look at this curve here, okay, which is taken from Physics Bro Q, it's a Dutch and Canadian website, okay, we have a certain pattern. On the x-axis, we have the angle, the angular deviation or abscissa, and we have the luminous intensity on the y-axis. Now, at the central bright fringe here, we have very high intensity, which is referred to as I0. Now, over here, we have zero intensity, referring to the dark fringe. In fact, referring to the center of the dark fringe, in fact. And from here, you can find the linear width or the angular width, since you are dealing with angles. Okay? So you need to know what are you reading here. If the x-axis shows angle, then the difference from here to here is an angle. So what I calculate by reading this is the angular width of the central bright fringe. Now, the second bright fringe here has an intensity of around 4.7%, 0.047 I0. So this fringe is much less intense than the central. So you notice this pattern. The central bright fringe is much more, it's wider than others, it's double the width, and it's definitely much more intense. So let's go now to solve an application. تقريبا خلصنا الأفكار الرئيسية بالديفراكشن. تعالوا نجمعهم كلهم بإكسرسايز مع بعض ونشوفوا. Application 2 حيكون من official exams. إذا عندك شامل روح معنا على دورة 2013 LS. If not, take a picture. Okay? حط هالإكسرسايز قدامك وهلا رح نروح على الحل step by step وبنحكي فيهم شوي. First, we'll read the exercise. There is a typo, في خطأ مطبعي أنا وعم بعرضها هلا انتبهت لها، هلا بنصحها مع بعض. Okay? A laser beam of light of wavelength lambda in vacuum falls normally, يعني perpendicular, to a vertical slit of width 0.3 millimeter. The diffraction pattern is observed on a screen placed perpendicularly to the laser beam at a distance 1.5 meter from the slit. Let L be the linear width of the central fringe meaning the central bright fringe. Angle theta 1. So this is the mistake that I was telling you about. It should be theta, not Q. Okay? Shown in the figure here, corresponds to the first dark fringe. For small angles, take sine theta equals tangent theta. أول شيء بتلاحظوه قبل ما نروح على الأسئلة، كل شيء كنا عم نحكي فيه بسياق الدرس بيرجعوا بيعطوكم إياه. So don't stress about the lesson a lot. It is supposed to be an easy lesson. لازم نعرف law of diffraction وكل الباقي بيصير قصص شوية geometry. Okay? Focus a lot on the geometry of how to solve problems. أكثر من أي part تاني بهيدا الدرس. State two differences between the central fringe and other bright fringes. Determine a relation between A, theta 1 and lambda. Establish a relation between A, lambda, L and A. Finally, given L, verify that lambda equals 630 nanometer. تقريبا كأنه حدا مسكني على ايدي بالسؤال وعم بيقول لي كل ستيب شو بدي اعمل. اوكي؟ رح نروح لنشتغل فيهم ستيب باي ستيب. ان شاء الله تكونوا اخذتوا صورة هون. اوكي؟ When I move to the second page ما رح فيها نرجع، رح نحكي عنهم step by step. So 1. State two differences between the central bright fringe and other fringes. We know that the central bright fringe is much more intense. So yes, it is much more brighter or it's simply brighter than others. And it has twice the width of other fringes. The width of the central bright fringe is double the width of any other bright fringe. Second question was, establish a relation between A, lambda, and theta 1. We went to the diffraction law, in which A sine theta m equals m lambda, m being an integer which is not 0. And angles are small, regardless of y. No need to prove them. It's given, if you recall, right? Okay. So, for the first dark fringe, we go to m equal to 1 because we are dealing with the first dark fringe as given. Then sine theta equals lambda over A. Using small angles, theta 1 equals lambda over A. Now, I've drawn here a figure just in case I need it, and in a step to prepare to part 3. So part 3 was to find the relation between A, L, D, and lambda, if I'm not mistaken. Right? Okay. So using the geometry of the figure, we have to link x to angles. So here is the figure which I have set up before. IOM is a right triangle. We know that trigonometry in right triangles gives us the property of using the tangent line. Tangent of theta 1 is opposite over adjacent, which is OM over IO. Now continuing, tangent theta 1 equals x1 over distance d, and x1, which is OM, is half L. So I replaced x1 by L over 2. So tangent theta 1 equals x1 over d, so that we don't do the same mistake again. Okay, again, using small angle approximation, tangent theta equals theta 1, then theta 1 is L over d. So notice that now I have two expressions for theta 1, this one and this one as well. Okay? Hence, lambda over A equals L over 2D, and this is the relation I'm asked about. Now, whether you prefer to write it in different form, L equal to lambda D over A, or anything else, it's not wrong. Okay? But I can stop here since I know that all I need is a relation right now. Last part, given L, find the value or verify the value of lambda if I'm not mistaken. So I went to this equation, I regrouped it, reordered it. Lambda equals A L over 2D, A times L over 2D, replacing values. A is 0.3 millimeters, so directly I multiplied by 10 negative 3. As we have seen in application 1, units should always be in one standard لحتى لي إذا بدي أعمل simplify أو أي شيء تاني يكون واضح قدامي. L is 6.3 millimeter كمان. D is 1.5, so 2 times 1.5. Replacing all of these, I get 0.63 times 10 to the minus 6 meter. هيدي بتكون هون وبالخطأ طلع تحت. Excuse me for this. Now, verification عم بيقلنا lambda in nanometers مش micrometer ولا 10 minus 6. نعرف نحن 10 نانو is 10 minus 9. انا عندي هون 10 minus 6. سو شو رح اعمل؟ بروح على الماثماتكس. اوكي 0.63 بضربها ب 1000 بتصير 630. وبالمقابل 10 minus 6 بحط لها 10 negative 3. بكون ضربت ب 1000 وقسمت ب 1000. ما بكون غيرت شيء. اوكي I get 10 minus 9 meters which is 630 nanometers. So هيدا sample exercise ممكن يكون شوي شردت ورغيت مثل ما بيقولوا كتبت كثير. It's fine. Okay. If you check in the شامل you can find the answer here a little bit with less explanation. Okay. You can skip some steps but if you wanna go over any idea الشرح بتلاقوه كامل هون. Okay. Now we go to the last section of this chapter which is known as the complementary effect. The complementary effect is an application or is something similar to diffraction given by a slit. But إذا بتتذكروا بس عملنا الإكسبيرمنت بآخر الإكسبيرمنت صورنا الليزر عم بيروح على شعرة وشفنا diffraction. That is what complementary effect is about. خلونا نقرأ شوي. When light falls on a fine opaque object, it produces a diffraction pattern identical to that produced by a slit with the same dimensions. يعني إذا بعتنا ضوء على opaque object مش opening مش فتحة مثل السلت بدل ما يكون عندي سكرين مسكر وبقلبه في فتحة لا I have an open window وبقلبه حاطين بلوك بعتنا ضوء عليه this block has the same dimension same width مثل الاوبننج اللي كانت قبل رح يطلع لي نفس diffraction pattern. هيدا صورة من سيت اب إذا بدكم مضويين على هي الشعرة ولكن الديفراكشن باترن وين؟ أوكي بتشبه اللي شفناها قبل. Now هون في a lecture or a video taken by MIT University بفرجونا الديفراكشن باترن. أوكي هيك في حال نحن ما قدرنا كنا نعمل اكسبيرمنت بنشوفها قدامنا. بتلاحظوا عم بدور على فاين لاينز شرطان أو خيطان أو whatever بس كثير رفاع يعني less than 1 مليمتر وفوق عم بشوف الديفراكشن فينا نغير من خيط لخيط لنشوف كيف بيتغير هيدا. however نحن بكل التارجت تبعنا بس نشوف انه في diffraction. now so in the complementary effect set up لكوينة هي الصورة انه بدل ما يكون عندك بلوك وبقلبها فتحة لا عندك شباك وبقلبه بلوك. اوكي complementary من هون اجت الكلمة. now لنشوفها أكثر check this we have a screen inside it we have an opening. okay Now the slit is away from the screen where we are studying diffraction a distance d. لاحظنا انه بالديفراكشن طلع عندي central bright fringe of width L. بالمقابل نفس الليزر استعملنا ضوينا على خيط على شريط a wire. Now كمان we observed diffraction at a certain distance away from the wire. Over here إذا عندي the width of the slit equal the thickness of the wire. So نفس ال A كأنه عم نستعمل نفس المسافة and same lambda لأنه نفس الليزر عم نستعمل. اوكي so بتلاحظوا لازم يطلع عندي L equal L1. هيدا المقصود بالcomplement بالidentical dimensions. so كل الاكسبيرمنت هيدا مثل الاكسبيرمنت هون بفرق بسيط بدل ما يكون opaque مع فتحة لا عندي window مع opaque object we obtain the same diffraction pattern. اوكي هيدا الكومبلمنتري ايفكت. Now أهمية الكومبلمنتري ايفكت أو الديفراكشن باي ثين وايرز مش الديفراكشن باي سليت فينا في عندها كذا ابلكيشن. اوكي واحدة منهم هي اندستري بالصناعة بشكل خاص بتصنيع شرطان الكهرباء. اوكي شركة عم تصنع شرطان بتعرفوا شريط كهرباء 5-6 كيلومتر يمكن بمد وبيلفوه ليضبوه بعدين صح؟ Now this wire should have the same thickness all that length. كيف فينا نعمل كنترول على سماكة هيدا الواير؟ اوكي؟ اللي بيصير هيدا الشريط هون بنضوي عليه ليزر لايت بيعمل ديفراكشن وهون بيكون عندي سكرين هاي السكرين عم بشوف الديفراكشن عليها بحط هون سنسورز. اوكي؟ Those sensors are capable of reading the light distribution. وبحسب دراستي أنا بسماكة هالشريط مثلا 0.2 ملم بده يطلع الديفراكشن هيك بالمسافة وبتعملوا الكالكوليشن ذاتها using the equation L equal to lambda d over A بهالبساطة. سو السنسرز بيقروا قد ايه عم يجي عليهم ضوء. اوكي؟ خف هيدا الضوء او ضوء زياده وسعه ال او صغرت ال، يعني A اللي هي A اللي هي الثيكنس اوف ذا واير تغيرت. هون الماشين بتعرف انه تغير الثيكنس وبتوقف. يو نو وات؟ سيشن 2013 اللي اشتغلناها كان فيها بارت ثاني اوكي بنفس السؤال بيركز على هاي الفكره. A manufacturer of thin wires wishes to control the diameter of his product. He uses the same setup mentioned in part A, application 2 عنا. Okay? D equals, lambda equals, but he replaces the slit by a thin vertical wire of thickness D. So غير ال A صارت D. He obtains a central fringe of linear width L1. L1 غير اللي كانت معنا قبل. It's okay. By the complementary effect, this wire produces diffraction just like a slit of the same thickness. So حتى ال complementary effect منك عايز تكون حافظه. عم بيقول لك انه بيطلع لي نفس الديفراكشن. So استعمل اللو اللي طلع معك قبل اذا ماني غلطان L equals 2 lambda D over A اللي هي هون شو صارت هلا؟ A اللي صارت هلا D. So I can use this equation to calculate the value of D. Okay? So هو لازم يكونوا مثل بعض. Okay? So solving the exercise منه صعب. Try to solve it. فيكم ترجعوا تروحوا على الدورة وتلاقوها. Okay? الحل بسيط كتير. حلوة. Next time فينا نعرض الحل، فيكم تسألوا أستاذكم، فيكم تعملوا تشيك اب بعد ما تنعرض هيدي الحلقة. رح نحط solution as a link after you watch this. Okay? Now by this خلصنا الديفراكشن. هون رح امشي على السولوشن بسرعه. اوكي ان شاء الله ما تكونوا استصعبتوا الدرس كثير. اوكي نكست تايم وي ميت رح يكون عندنا تشابتر جديد. بقى بتمنى عليكم بس مشوا ورا التشابتر مره ثانيه. اهم ايكويشن بدنا اياها A sin theta equals M lambda. جمعوا الرولز. بهيدا الدرس geometry is very important، نركز عليه اكثر من شيء ثاني. اوكي حلوا كم اكسرسايز. next time when we meet in interference بنعمل هيك ريكاب على اللي اشتغلناه هون ونبلش تشابتر جديد. Until then please stay safe ونهاركم سعيد.